welcome to True Projects. In this video, we are going to explain about the project entitled as Real-Time Anomaly Detection in IoMT Networks using Stacking Model and a Healthcare-Specific Dataset. So before getting into the video, let me give you the brief description about the project. The project focuses on identifying unusual or suspicious activities in connected healthcare devices as they happen. Using a stacking model, a machine learning ensemble technique that combines multiple algorithms, improves detection accuracy, and reduces false alarms. A healthcare specific dataset ensures the system understands medical network behavior and device patterns. This approach helps enhance patient safety, protects sensitive health data, and maintains reliable healthcare services. Coming to the abstract explains that the Internet of Medical Things helps improve healthcare by allowing medical devices to collect and share patients' data in real time, which supports better monitoring and treatment. However, because many devices are connected to networks, they become vulnerable to cyber attacks and unusual activities that may threaten patient safety and data privacy. To solve this problem, the project proposes a real time anomaly detection system that uses a stacking ensemble machine learning model which combines multiple algorithms to increase accuracy and reduces false alarms. The system analyzes network traffic and healthcare related data to detect abnormal behavior or possible attacks quickly. Overall, the goal is to make IoMT networks more secure, reliable, and safe for healthcare services. Coming to the existing system, the existing IoMT security systems mainly detect abnormal activities using traditional machine learning methods or rule based intrusion detection systems. This approaches usually depend on a single algorithm such as support vector machines, decision trees, or k nearest neighbors, which may not effectively identify complex or new types of cyber attacks. Many current solutions also uses general network data sets that do not reflect the unique behavior of healthcare devices, resulting in lower detection accuracy and more false alarms. In addition, most of these systems do not support real-time monitoring, which is a major limitation because delays in detecting threats can be dangerous in critical healthcare environments. Coming to the proposed system or base paper work, the proposed system focuses on improving the security of IoMT networks by using a real time anomaly detection method based on a stacking ensemble learning approach. In this method, several machine learning models such as random forest, gradient boosting, and support vector machines are combined, and a meta classifier is used to produce a more accurate final decision. The system is trained using a healthcare specific IoMT data set so that it can better understand the normal communication patterns of medical devices. By continuously monitoring network data and extracting important features, the system can quickly detect unusual activities or cyber threats. Overall, this approach increases detection accuracy, reduces false alarms, and provides a reliable and scalable security solutions for healthcare environments. Coming to the data set, we have used two different data sets. Among them, the first one is ML based network intrusion detection system data set. The ML based NIDS data sets developed by the University of Queensland are widely used for research in intrusion and anomaly detection. This dataset consists of labeled network traffic collected from both real and simulated environments and are processed into NetFlow and flow based formats suitable for machine learning applications. They include normal traffic as well as various types of cyber attacks such as DOS, DDoS, brute force attacks, scanning, and botnet activities. Available in multiple versions with increased number of features. The datasets provides detailed traffic characteristics that helps improve detection accuracy. Because of their realistic traffic patterns and comprehensive labeling, these datasets are highly suitable for building and evaluating real-time anomaly detection systems, especially for IoT and healthcare network security. Second, we use diabetes binary health indicators dataset. It is known as BRFSS 2015 dataset. The Diabetes Binary Health Indicators dataset is a healthcare dataset collected from the 2015 Behavioral Risk Factor Surveillance System conducted by the US Centers for Disease Control and Prevention. It contains survey data from more than 250,000 individuals and includes information about health conditions, lifestyle habits, and demographic factors related to diabetes. The dataset has around 21 features such as BMI, smoking, physical activity, cholesterol levels, blood pressure, diet, access to healthcare, and income. It targets variables in binary, indicating whether a person has diabetes or pre-diabetes. This dataset is widely used in healthcare analytics and machine learning to build and evaluate models for disease risk prediction and health related classification tasks. Coming to the novelty or extension or enhancement or improvement. As an extension to the main system, a soft voting ensemble classifier is developed by combining XGBoost and random forest modules. This approach uses the prediction probabilities for both models and selections, the final output based on their combined confidence. Since XGBoost is strong in handling complex patterns and random forest is effective in reducing overfitting, their combination improves overall detection accuracy and robustness. This ensemble performs better than the original stacking model and other existing methods, making it a stronger solution for detecting anomalies in IoMT network. Furthermore, to make the model's decision more understandable, explainable AI techniques such as LIME and SHAP are applied. These methods help identify which features have the most influence on the predictions made by the model. By providing clear insights into how and why a particular anomaly or attack is detected, they increase transparency, trust, and reliability, which is especially important in healthcare related systems. Additionally, the Flask framework is used to develop a simple user interface that allows users to input data and receive predictions from the trained machine learning models. This interface makes the system more user friendly and practical for real world use. A healthcare and network administrators can easily test inputs and monitor results without needing technical knowledge of the underlying algorithms. Coming to the flow of the work, first we have import the packages. In this step, all the required Python libraries are imported such as NumPy, Pandas, Scikit-learn, XGBoost, TensorFlow, Keras, Matplotlib, and Seaborn. These packages are used for data handling, preprocessing, model building, evaluation, and visualization. Next, load the dataset. Two datasets are loaded into the system. One is UNSW NB15V3 for network intrusion and anomaly detection, BRFSS 2015 for healthcare related features. These datasets provide both network traffic information and health indicators for building the proposed detection framework. Next, pre-processing. Data cleaning is performed to prepare the datasets for analysis. Unnecessary or irrelevant columns are removed. Labels are mapped into meaningful categories. Missing or null values are removed to avoid errors during the training. Next, label encoding. Categorical features such as protocol types or services names are converted into numerical form using label encoding so that machine learning models can process them. Next, feature selection. Important features are selected to improve models' performance. Recursive feature elimination with XGBoost is applied on the UNSW dataset to choose the most relevant network traffic features. Next, concatenations of dataset. The selected important features from the UNSW dataset are combined with the BRFS healthcare dataset. This creates a hybrid dataset that includes both network and healthcare related attributes. Next, sampling. SMOT is used to balance the dataset by increasing samples of minority classes. This helps reduce bias and improves detection of rare attacks. Next, normalization. Standard scalar is applied to normalize feature values so that all features are on the same scale. This improves models' accuracy and training stability. Next, train test split. The dataset is divided into training and testing sets. The training data is used to train the models, while the testing data is used to evaluate their performance on unseen data. Next, build the models. Multiple machine learning and deep learning models are trained for UNSW NB15 dataset, like logistic regression, random forest, XGBoost, K nearest neighbor, support vector machine, artificial neural network or MLP, isolation forest that is known as ISOF, and proposed models are stacking classifier which combines XGBoost random forest ANN with XGB as final estimator, and extinction soft outing ensemble which combines XGB, RF, MLP. For concatenate data, multi-class we have used logistic regression, random forest, and XGBoost. For binary, we have used logistic regression, random forest, XGBoost, KNN, SVM, ANN, ISOF stacking model, and outing ensemble. Next, evaluation. Model performance is measured using confusion matrix and classification report. Metrics such as accuracy, precision, recall, FN score, ROC, AUC, false positive rate, and test time. The results are compared both numerically and uses visual graphs. Next, save the best model. The model that provides the highest performance is saved so that it can be reused later without retraining. Next, explainable AI, Lime and Sharp. Lime and Sharp are used to explain how the model makes predictions by showing which feature influence the output most. This improves transparency and trust. Coming to the front end, a user interface is developed using Flask, including registration and login functionalities supported by SQLite database. The trained model is connected to the front end so that it can be learned patterns from the dataset to make prediction. User enters feature values through the interface, such as network or health related parameters. The entered data is pre processed in the same way as the trained data. The pre processed input is passed into the saved model to predict whether the behavior is normal or anomalous. The prediction results is shown to the user through the front end interface. The algorithms used are for UNSW NB15, we used logistic regression, random forest, XGBoost, K nearest neighbor, support vector mission, artificial neural network or MLP, ISOF. For proposed, we use stacking classifier XGB, RF, ANN with XGB final estimator. And as an extension, outing with soft outing we have done, which includes XGB, RF, and MLP. For concatenate data, multi-class we have used logistic regression, random forest, and XGBoost. For binary class, we have used logistic regression, random forest, XGBoost, K nearest neighbor, support vector mission, artificial neural network or MLP, isolation forest, stacking, which combines XGB, RF, ANN with XGB final estimator. And as an extension, we have done outing with soft outing, which includes XGB and random forest. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language Python, front-end framework Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain the algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. In the Anaconda prompt, this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the Flask framework and paste it in any web browser. I prefer Chrome, so that the home page of the project should now be displayed in the browser. This is a front-end built using the Flask framework. In this page, we have Home button, Access Account button, and Get Started button. Firstly, click on Get Started button so that registration form will be open where you need to create an account for user authentication like full name, username, mail ID, contact number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and login.html will be opened where you need to access the application with the help of username and password. Then click on sign in. The prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and logout button. Firstly, click on prediction button so that make a prediction form will be open where you need to enter the information given below to get a prediction. So let us give the input values. First, diabetic binary. No. High BP. Yes. High cholesterol. Yes. Cholesterol check. Yes. BMI is 40. Smoker. Yes. Stroke. No. Heart disease or attack? No. Physical activity? No. Fruits? No. Veggies? Yes. Heavy alcohol consumption? No. Any healthcare? Yes. No doctor because of cost? No. General health is 5. Mental health is 18. Physical health is 15. Difficulty in walking? Yes. Gender? Female. Age? 9. Education? 4. Income? 3. Flow starts value is 142 14200000000. Flow start value is flow ends value is L4 destination port value is 53. L7 protocol value is 5. TCP flag value is 0. Client TCP flag value is 0. Minimum TTL value is 31. Maximum TTL value is 31. Longest flow packet value is 89. Retransmitted out packets value is 0. Click on predict button so that the given values are pre-processed and the output is displayed as attack detected. And the attack type is of fuzzers. The confidence level is of 100%. Attack probability is 100%. Normal probability is 0%. Here we have security alert and recommendations for fuzzer attack. Like immediate actions required are given below. Safety precautions are given below. Best practices and tips are given below. Now click on make another prediction so that the prediction form will be opened again where you need to enter the values of diabetes binary is no. High BP, no. High cholesterol, no. Cholesterol check, yes. BMI is 33. Smoker, yes. Stroke, no. Heart disease or attack, no. Physical activity, yes. Fruits, yes. Veggies, yes. Heavy alcohol consumption? No. Any healthcare? Yes. No doctor because of cost? No. General health is 2. Mental health is 0. Physical health is 2. Difficulty in walking? No. Gender? Male. Age? 8. Education? 6. Income? 8. Flow ends value is L4 destination port value is 8088. L7 protocol value is 0. TCP flag value is 18. Client TCP value is 18. Minimum TTL value is 254. Maximum TTL value is 255. Longest flow packet value is 40. Retransmitted out packet value is 0. Click on predict button so that the given values are pre-processed and the output is displayed as normal detected, which means for the given values, it is normal detected. Confidence level is 67.03%. Attack probability is of 32.97 percentage and normal probability is of 67.03 percentage. And system status and recommendations like current status of system is given below, preventive measures are given below, and maintenance tips are also given below. And now click on graphs button so that graph 1 and graph 2 will be open. Let us check one by one. First, graphs 1. In this first, we have attack category distribution graph. The graph shows the distribution of different attack categories in dataset where benign dominates with about 94.57 percentage of all the records. All attack types such as exploits, fuzzers, generic and others appear in very small portions. This indicates a highly imbalanced dataset where normal traffic is much larger than malicious traffic. Next, we have feature importance RFE selected feature graph. The graph shows the feature importance of RFE selected features where DNS query type has the largest influence on the model's prediction compared to the other features. Features like shorted flow packet and maximum TTL contributes moderately, while the remaining features have minimal impact. This indicates that a few key network traffic attributes plays a major role in detecting anomalies. Next, we have Outing ensemble confusion matrix graph. The confusion matrix shows the performance of the outing ensemble model by comparing the true labels with the predicted labels. Most values are concentrated along the diagonal, indicating that the model correctly classifies the majority of samples across different classes. The smaller off diagonal values represents misclassifications, showing that only a few instances are incorrectly predicted. Next, we have accuracy graph. This graph compares the accuracy of different machine learning models used in this study. Ensemble approaches like stacking and the extinction outing model achieves the highest accuracy, outperforming individual models such as logistic regression, random forest, and XGBoost. Isolation forest shows the lowest accuracy, indicating it is less effective for the classification task. Next, we have precision graph. The graph shows the precision value of different machine learning models, indicating how accurately each model predicts the positive classes. The stacking and extinction outing ensemble models achieve the highest precision, meaning they produces fewer false alarms compared to the other models. Models like KNN and isolation forest have low precisions, showing less reliable positive predictions. Next, we have recall by model graph. The graph compares the recall of different models, showing how well each model correctly identifies actual attack or anomaly cases. The stacking and extinction outing models achieve the highest recall, meaning they detect most of the true threats. In contrast, models like KNN and isolation forest have lower recall, indicating they miss more actual anomalies. Next, we have F1 score by model graph. The graph shows the F1 scores comparison of all models, which reflects the balance between precision and recall. The stacking and extinction outing ensemble models achieve the highest F1 scores, indicating the most balanced and reliable performance. Models like KNN and isolation forest have lower F1 scores, showing weaker overall detection effectiveness. Next, we have ROC AUC graph. The graph compares the ROC AUC scores of different models, showing their ability to distinguish between normal and attack classes. Most models, especially stacking, extinction outing, SVM, and XGBoost, achieve scores close to 1, indicating excellent classification performance. Isolation forest has a noticeably lower ROC AUC, meaning it is less effective at separating the classes. Next, we have FPR graph. The graph compares the false positive rate of different models, indicating how often normal traffic is incorrectly classified as an attack. Random forest and the stacking model shows relatively lower FPR, meaning fewer false alarms. Models like SVM and isolation forest have the higher FPR, suggesting they misclassify normal instance more frequently. Next, we have test time graph. The graph shows the testing time required by each model to make predictions. KNN and isolation forest take significantly more time compared to the other models, indicating slower prediction performance. Most other models, including the ensemble methods, have very low test time, making them more suitable for real time detection. Next, we have explainable AI SHAP graph. This is a SHAP summary plot showing which features most influence the model prediction. Each dot is a sample. Position on the x-axis shows whether the feature pushes the prediction up or down, and color shows low to high feature values. Features at top has the largest overall impact on the model. Now let us check with graphs too. In this first we have feature importance RFE selected features graph. This bar chart shows feature importance from RFE, where higher bars means greater influence on the model. Maximum TTL dominates the model's decision, contributing far more than any other features. The remaining features have relatively minor and similar impact on prediction performance. Next, we have confusion matrix graph. This confusion matrix shows near perfect classification performance of the voting model. Most samples are correctly classified with only two misclassifications per class. This indicates very high accuracy and balanced performance across both labels. Next, we have accuracy graph. The bar chart compares model accuracy across multi-class and binary classification tasks. Binary modules generally perform near perfect accuracy, especially ensemble methods like stacking and voting. Multi-class accuracy is lower overall, with logistic regression and isolation forest performing notably worse than tree-based and ensemble models. Next, we have precision by model graph. The graph shows that precision is highest for binary classification models, with most achieving near perfect scores. Ensemble methods and ANN SVM performs best, while multi-class logistic regression and isolation forest shows noticeably low precision. Next, recall by model graph. The recall scores indicates the binary classification models consistently achieving near perfect performance, effectively capturing almost all positive cases. In contrast, multi-class logistic regression and isolation forest shows lower recall, while ensemble methods maintain the strongest and most balanced recall overall. Next, we have F1 score by model graph. The bar chart compares F1 scores of different machine learning models for multi-class and binary classification. Binary models generally outperform multi-class ones, with ensemble methods like stacking and voting achieving the highest scores. Isolation forest and logistic regression shows noticeably lower performance. Next, we have AUC by model graph. The bar chart shows the AUC scores of different machine learning models across multi-class and binary tasks. Binary classifiers, especially ensemble methods like stacking and voting, achieves near perfect AUC, indicating excellent class separation. Logistic regression and isolation forest have comparatively weaker performance. Next, we have FPR by model graph. The graph compares the false positive rate across different machine learning models. Binary classifiers such as LR, RF, ANN, and SVM shows near zero. FPR indicating very few false alarms. In contrast, logistic regression and isolation forest exhibits highest FPR. meaning more false positives. And then click on Logout. So finally, this project successfully demonstrates an effective real-time anomaly detection framework for IoMT networks using a stacking ensemble learning model and a healthcare-specific dataset. By combining multiple machine learning algorithms and healthcare relevant features, the system achieves higher detection accuracy and reduced false positive compared to traditional methods. The integration of explainable AI and a user friendly interface further enhance trust and practical usability. Overall, the proposed approaches provides a reliable and scalable security solutions for safeguarding IoMT based healthcare environments. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.